Good evening, everyone, and welcome to the 11th session for the course Introductory course in Real Analysis. So, in today's session, we'll be uh, solving problems which are related to differentiability of function, related to some properties of that, and some limit problem as well. We're using L'Hopital rule, what you have learned. Okay, so to begin, let's start with this problem. Okay, so suppose you have a function f which is defined in this fashion. Okay, so it's 0 on minus 1 0 and it's 1 after 0. Okay, so the question is, does there exist a function g such that its derivative is f? Okay, so do you know how to solve this, or what do you think, such function will exist or not? Any idea?
Continuous function.
Sorry.
F is not a continuous function.
Correct. So
the derivative does not exist.
no, so you don't have to look for the derivative of f, right? So you have to find a function g whose derivative is f. So f is not differentiable, that is fine. We are not talking about
Riemann integrable. Riemann.
How do you come with integrability? I couldn't understand. Can you just explain more?
If we integrate f, we will be getting g, no, sir?
We will be getting 1 if we integrate f. So what does that mean? I mean, I cannot see your answer. So if I integrate f, I'll get 1. So from there, how can you conclude that whether such function exists or not?
You have asked to find whether there exists a function g such that g dash of x is equal to f of x. So when I integrate on both sides,
Correct.
g of x is equal to integral f of x.
Correct. So from here I'll get that g prime integral is same as f integral, and this is 1, and this will give me g of 1 minus g of minus 1, right? So how?
Yes, sir.
So what does this mean? So from here, how we are concluding the answer? So I got this thing. Now this is not giving anything, right? Or maybe you can. Okay, so what is your guess? So you are saying that there will exist g, or where there will not exist g? First, let us see that. So is the answer positive or negative? I mean, does there exist or there does not exist? What is your answer? I mean, what you are
There
trying
does
to.
not exist.
Okay, you are saying there will not exist such function g. Okay, fine. So from here, how can you conclude it?
I can't be able to proceed, sir.
Okay. So actually, what you said initially is some way correct. I mean, not exactly that thing, but you noticed the very good thing that okay, if is not continuous, that is fine. But suppose, how should I say, that you know one property, that derivative of a function always satisfies this intermediate value property, which is the Darboux theorem, right? What does Darboux
Yes, sir.
theorem says? That intermediate value true is true for derivative. Now what you have noticed is that this f is not continuous, and in fact it does not uh, satisfy the intermediate value property, because it is just taking two values, 0 and 1. So whatever comes in between 0 and 1, it is not attained, right? So f does not have intermediate value property. Now suppose such function exists, that would mean that g prime has intermediate value property from the Darboux theorem. Correct? but we know that f does not have. So from there you can conclude that such function does not exist. Did you get the argument? Okay. Okay, so I'll just write the answer. So we'll prove by contradiction basically. So suppose, if possible, suppose there exists a differentiable function g on minus 1 1 such that g prime is equal to f. Okay, note that g prime at minus 1, right? So at minus 1 it is attaining the value 0, and g prime at 1 is taking the value 1, right? So by Darboch's theorem, for all alpha which lies between 0 and 1, right? So for all alpha, okay, so for all alpha belonging to minus 1 comma 1, there exists some x alpha in the domain which is minus 1 comma 1 such that okay, it should be open, sorry, this should be 0 1, there exists minus 1 1 such that g prime of x alpha is equal to alpha, right? And this means that f of x alpha is alpha, but we know that if alpha is in 0 1, f cannot take such values, right? So this is a contradiction. So I mean, who should I write? So, but this is not true, right? But this is not true, as f only takes the value 0 and 1, takes the value 0 and 1, hence our assumption is wrong. Is wrong. So such g cannot exist. Okay, so this was just a very easy problem based on this Darboch's theorem, correct? I hope it's clear. Okay, so now let's move to this problem. So over here you have to evaluate the limits of these given functions. Okay, so these are all the right hand limits. Okay, and the reason being that, like, for negative x this does not make sense. Okay, this might not, because we are dealing in real system. So suppose x is minus 2, so minus 2 raised to the power minus 2 would be or let's say minus 1 by 2. If I take, that would mean 1 by root of minus 2, 1 by 2, right? So this does not belong to a real number, so that's why we are just focusing on the right hand limits. Okay, so the same is true for this as well, because if x is negative, okay, so this, suppose x is, I take let's say 2, right, or root 2. If I take minus root 2, then again there will be a problem because of this minus root 2 of this. Okay, so this would not make sense, that's why we are just dealing with the right hand limits. Okay, so how do you deal with such problem? Okay, so do you know any idea? Like, I think I have mentioned once while dealing with the sequences. So do you have any idea how to deal with such problems? So how do you deal?
If there is a power, we have to take log.
Correct. Yeah, very true. Okay, so and okay, so most important property is that the log is continuous function, right? So okay, I'll tell that one. So this is the property, so let me write it. So if suppose fx is log of x, okay, then what you know that f is continuous. So if I take limit x going to, let's say, x naught f of x, then this is same as f of x naught. Okay, so I am dealing with x greater than 0 and x naught is also greater than 0. Okay, so this is one of the important property, that if you take log, it's basically, it is like this, maybe f of limit x going to x naught, right, f x, correct, so which is f of x naught. So this is the property of continuous function, that you can take the limit inside, that's all. Okay, so this is one of the important property, okay, that we'll be using over here. Okay, so over here, so let's start with this first problem, right? So we'll denote this function x raised to power x by some another variable, so maybe let's denote it by y. So y of x is nothing but x raised to the power x. Okay, now if I take log, so it will be log of y of x is actually x times log of x. Okay, okay, fine. So now we'll talking about the limit of this function. Okay, so let's look at the limit of this function. So limit x going to 0 plus x times log of x. Now you notice this is nothing but, so you can write this, you see this is 0 and this is going to minus infinity, right? So it is 0 times infinity, so this can be written in another way. So what one can do is 0 plus, and then I'll write it as log of x, and then here I'll have 1 by x. Okay, so now both are going to, it's kind of infinity by infinity form, although log is going to negative of infinity, so it's sort of infinity by infinity form. So what we can do is we can use L'Hopital, right? So we'll try to use the L'Hopital over here. So this is this. Now log of x, if I take the derivative, I'll get 1 by x, correct, and for 1 by x I'll get minus 1 by x square. Okay, so now it reduces to limit x going to 0 plus, and then you have minus of x, correct, and this is nothing but 0. So far we have evaluated.
Sir, what is log 0, sir?
Log 0 is not defined, right? Log 0 is not defined. So so let me show you the graph. So the graph goes like this, like at 1 it is 0, and it's like asymptotic at infinity as x goes to 0. So the graph of log is like this, right? So log of 0 is undefined, okay, but it has this kind of behavior. Okay, and that's why actually we are talking about the limit. If it is defined at 0, then limit does not make sense, right? So it is as it is. So here we are talking about the limit because it does not make sense at 0. Okay, so this log, whatever I said, this is continuous on open 0 infinity. 0 we don't include, that's why I've written x greater than 0. Okay. Okay, so what we have got is that the limit of this is turning out to be 0. So in other way I can say that limit x going to 0 plus y of log of y of x is becoming 0, right? So as I mentioned above, so I can write this as log of limit, just a second, limit x going to x 0 plus y of x. So this is kind of composition. So log and y we are composing. Okay, so this is composition of two functions, but the same thing you can do here as well. So f compose g, if f is continuous you can take the limit inside, right? So this is this, and f compose g of x. So you can, maybe you can check that if f is continuous. Okay, so this maybe you can take it as an exercise if you want. So this would be f of limit x going to x naught g of x. Okay, so if f is continuous. Okay, so over here I can do the same thing, because since log is continuous I can do so, and this is equal to 0. Now I'll just take the exponential. Okay, so what I get is limit x going to 0 plus y of x is nothing but 1, right? So this is how you can say that limit x going to 0 plus x raised to the power x is 1. Okay, so this is how you can get the answer. So whenever you have power x in the power, you can take the log and then try to deal with it. Okay, okay, now let's come to this, the second one. So the second one is limit x going to 0 plus sin x by x, and then you have 1 by x square. Okay, so again, like in a similar fashion you can do. Now I'll be doing much more vaguely rather than writing it so precisely. So here the reason is that since log is a continuous function, okay, here you also make sure that this y of x is greater than 0, okay, from here. So that's why this log makes sense. Okay, you cannot take log every time. Since over here we are dealing with this is a positive quantity, we can take log. Okay, so here what I'll just try to write it much more vaguely. So suppose this limit is a, okay, sine of x upon x by 1 by x square. Now I'll just take log. So log of a would be limit x. So how should I write? So maybe, so you take log. So you can understand, since log is continuous, I can write this as limit x going to 0 plus log of sin x by x 1 by x square. Okay, so over here also you can notice that since I am talking x in the neighborhood of 0, I know that sign is positive, right? So this quantity is greater than 0 in neighborhood of 0, right? So in a small neighborhood we know, maybe in, not I should say in neighborhood of 0 because it includes minus region as well. So maybe I can say 0 comma delta, right, for small delta. So we know it is a positive quantity, so we don't have to worry about that. So it's, the whole thing is positive, right? This is positive, so everything is positive. I can take log. So what I am getting is this one, and this is again I have used that the log is continuous function. That's why we can do that, correct? Okay, so now again, like you just have to use this property of log. So I'll get 1 by x square outside, and then you will have log of sine of x upon x, correct? Now, okay, so you can see this one, see this limit. Okay, let's look at this term. Okay, so this term is like limit x going to 0 plus sin x upon x, and you know that this limit is equal to 1, right? This is what we have seen. Again here you can use L'Hopital, and then you will get that this limit is 1. Okay, and log of 1 is 0. Okay, so this is 0 by 0 form. Okay, so we don't have to use that sign is bounded, so because this limit is finite. Okay, so we have this 0 by 0 form. So now I can use this L'Hopital. Okay, so let's see how it goes. So the denominator derivative is clear that it is going to be 2x. Okay, and about the numerator you can see that it can be written as, so 1 log derivative is 1 by that, so it would be x by sine of x, and then the derivative of sine x by x is given by, so okay, again I'll have to use this fraction. Okay, anyway, so sine x I will take outside, and then 1 by x derivative would be minus 1 by x square, then plus, then sine derivative is cos, and then 1 by x. Okay, so now if I proceed further, okay, so let us look at how it's going to be. So sin x, maybe we can do a bit of separation because this limit I know it exists, so maybe I can write this as x by sin x. Okay, and again you can see that limit x going to 0 plus 1 by x square. I can take the this LCM, so what I will get is x cos of x minus sine of x upon x square, and then in the denominator you have 2x. Okay, yeah, is it okay? Or maybe this you can cancel, and then what you get is, so divided by 2x, so I think here you will get x cube, right? So 2x I am taking with this, so what I get is, maybe I can write this, so this would be 2x cube. correct. Okay, so now here what you can do, so why I have written this, so there should be proper justification, otherwise this does not make sense. We know that the limit of product exist, I mean is equal to the product of their limits if both the limit exist, otherwise we cannot do so. Okay, so over here, so maybe let me write the reason. So we know that this limit x going tending to 0 plus this x by sin x exists and this is equal to 1. Let's look at the other one. So this limit x going to 0 plus x cos of x minus sin of x upon 2x cube. Okay, so this is going to be so here you can see this is 0 by 0 form. Sine of 0 is 0 and this is 0 and this is 0. So again I'll use the L'Hopital rule. So what we have is, so this would be x and cos derivative would be minus sine, so it would be minus sin x plus, and then you will have this cos of x, and then again this sin x would, the derivative would be cos of x, so that would cancel, cos of x, and then you have 6x square, correct. Again you see that this is going to be 0 by 0 form, so I'll use L'Hopital again. You will have x tending to 0 plus, here again I'll have minus x, sine derivative would be cos plus, and then minus of sine of x again, and then you will have just a second, yeah, and here you will have 12x, again 0 by 0 form, again L'Hopital I'll use. So here I'll get minus x, cos derivative would be minus sine, so I'll get sin x, and then you have minus cos of x, and here again minus cos of x, correct, and here you will have 12. Okay, is there some mistake, because there should be some sign change, just a second. So here I have minus x sin x plus cos x, and then you had minus cos x, correct. This cancelled out. Now I have minus x cos x minus sin x, fine, this was 0 minus 2, it should be 0, it seems. Can you find mistake somewhere? Did I something wrong? Do you see any mistake over here? I don't know, I cannot see. Okay, whatever comes up, then I think okay, it should not be 0 then. So then I'll have here minus 2, so minus 1 by 6. Okay, so what the answer would be, so since both the limit exist, okay, so we can separate this up, we can write it as a product of their individual limits, and ultimately what we get is 1 times minus 1 by 6, so this is minus 1 by 6. Okay, so did you check this calculation? Is it okay? It seems to be, to me at least, I don't know. Okay, if it's okay, otherwise whatever comes up that you will have to write, that's all. Okay, so this is how you can deal here. So what you have got is a log of a is minus 1 by 6, right? So what will be the value of a? So a would be e raised to the power minus 1 by 6, and this is your answer. So this limit is nothing but exponential of minus 1 by 6. Okay, so this is the value of the limit. Okay, so now let's move to the next problem. Okay, so over here you have been given that f is a C2 function. Okay, so C2 means, I should mention here, so this C2 means that f is differentiable, f prime is differentiable. So C2 means basically two derivative exist and the second derivative is continuous. Okay, so f prime, f double prime exists, okay, and the last derivative is continuous. Okay, so this is what you have in your hand. The question is that suppose this situation that f is a C2 function, then this limit, okay, this limit is nothing but the derivative of f, double derivative of f at x. Okay, so this is what you have to prove, that if my function is a C2 function, then this limit will be equal to the double derivative. Okay, okay, so now let us try to see how we can prove. Okay, so do you have any idea like how you can deal with such problem?
First, we have to find f dash of x.
Correct. So
Limit h tends to 0, f of x plus h minus f of x divided by h.
oh, okay, that way you're saying. Okay, so let me proceed what you're saying, and then you will see what is the problem. Okay, so as you suggested, I will just write f of x plus h minus f of x, right? And then I'll pair this f of x minus h minus f of x, and then upon h squared, so you're saying that I'll divide it by here, so like this maybe h, and then I'll have 1 by h, correct? Is this what you mean?
For f dash of x, we will be having limit h tends to 0, f of x plus h minus f of x divided by h. Isn't it, sir?
Yeah, this one you are saying, right?
Or f dash of x.
Yeah, so you are saying this will become f dash of x, right? This is what you are saying. Now what about this one? Again this will be f prime of x, right? Okay, I think, okay, so what you said I'll just write. So you agree that this f prime of x is going to be limit h going to 0, f of x plus h minus f of x upon h, right? This you agree. Now let's do a change of variable. So I'll denote h, replace h by minus of, let's say, h tilde. Okay, so this will be limit. Now since h goes to 0, h tilde will also go to 0. Okay, so then I can write f of x minus h minus f of x, and then here I'll have minus h of tilde, sorry. Okay, so I'm replacing h by h tilde. Okay, is this okay what I'm writing? Now this is nothing but you can take minus outside, correct? So what you have it, limit, okay, limit h tilde going to 0, f of x minus h. So I'm just again, okay, let's go with this only, minus f of x and h tilde. Okay, so what you saw, that's minus, this limit is going to be minus of f prime of x, right? From here you can clearly see that f prime of x is minus of this thing. Okay, so now you see this is equal to, I can write limit, okay, but there is a problem, I mean, okay, so how should I say? So okay, in this way maybe. So you see this limit, if you look at this whole thing, so the, maybe I can write it in this way maybe, by h. Okay, so the numerator you can see that this is going to 0 and the denominator is also going to 0. Okay, right, because here also if you take limit it is going to 0. Okay, so you cannot just directly deal with this. So now what you can do, So see, from here you cannot conclude it. You are just saying that this will be 0 by 0 form in the limit, right? So this is not giving you answer because here you have h. If this was not there, then you can say that this is going to be 0. But just because this is h is present, so this is coming out as a 0 by 0 form. Okay, so this sort of motivates us that okay, we can try to use this L'Hopital rule. Okay, so in this way we can proceed. Okay, so now let me go to the solution. So this is one way of solving it, that okay, I'll just use L'Hopital and then try to see where it lands up to. Okay, okay, so this was anyway, this is this kind of motivation. Okay, so now let's go to the solution part. So we have this limit h going to 0, f of x plus h plus f of x minus h and minus 2 of fx, and then in the denominator we have h square. Now what we have seen here is that this is as 0 by 0 form, right? So we know that this is 0 by 0 form. So now what we can do is we can use L'Hopital rule, correct? So what I can write is L h going to 0. Now the derivative what we'll do is with respect to h. Okay, so this will have, so in the denominator we have 2h, in the numerator we have f prime of x plus h into 1. The derivative of x plus h will be 1. Then we have f prime of x minus h, and then derivative of x minus h would be minus 1, and then minus 0 because f does not, this term does not involve h. Okay, so we are differentiating with respect to h. So this is what we get. Now this is nothing but limit h going to 0, f prime of x plus h minus f prime of x minus h upon 2h. Again, if you look at this one, now since, okay, actually there is a direct way of looking that okay, it is going to be 0 by 0 form, is that you see, since f is differentiable, so f is continuous. So this limit h going to 0, f of x plus h is nothing but f of x. Okay, same with this one, this is f of x, so this is 2fx minus 2fx, so this is going to be 0. Okay, so this directly also you can see that this is 0 by 0 form, so you don't have to go through this one. But since C was thinking, okay, so what C has in mind is that okay, we can just take the limit, and using the definition we can conclude that this will be turned out to be the double derivative, because from here one, the way it has been written, it seems that this is f prime, right, and this is also some sort of f prime. So the difference of f prime at some point and the difference of f prime will again give me the double derivative. So this is what I guess C was suggesting, but this is not how it turned out to be. Okay, so over here we have this 0 by 0 form. Again, what we can do is, here we know that f prime is continuous, so again you see that f prime of x plus h will be f prime of x, here it will be minus of f prime of x, so again this is 0 by 0 form, correct? So now what you can do, again you can use L'Hopital. So what you get is limit h going to 0, this will be f double prime of x plus h minus f double prime of x minus h, again minus 1, so it will be plus, and in the denominator we have 2. Okay, and this is nothing but, just now you take the limit, so you will get f double prime of x plus f double prime of x by 2. So now why we can do that, because my double derivative is continuous, so that's why we can do so. So this is since f double prime is continuous. Okay, and this will give you f double prime of x. Okay, so this is one way of going. The other way could be, so as she mentioned, like it seems like it's kind of derivative. Okay, so this, if you want to use this kind of idea, so what you can do is you can use the Taylor expansion. Okay, so maybe I'll just give a hint. So the hint could be like this. So this f of x plus h can be written as f of x plus h times f prime of x, and then plus h square by 2. Okay, and then f double prime of, let's say, x theta, where theta will be lying between 0 and 1. No, x plus theta h. Okay, where theta belong to 0, 1. So that this term belong between x and x plus h. Okay, in the same way, what you can do is f of x minus h, you can write f of x minus h f prime of x plus h square by 2 f double prime x minus theta h. Now if you just sum it up, because here you have this summation, so f of x plus h plus f of x minus h will be equal to 2 of fx. This will cancel out, and then you have h square by 2, and then you have this f double prime x plus, so let's say this is theta bar, so theta h plus f double prime x minus theta bar h. Okay, now you can just divide by, you can take this here and then divide by h. So what you get is f of x plus h. So I mean this whole quantity will be equal to, this one will be equal to what will be that, so h by 2, and then you have f double prime x plus theta h minus, sorry, plus f double prime x minus theta bar x, sorry, h. Okay, now once you have this, now again this is a very, in a very good shape. Okay, just a second. Okay, so I have to divide by h square. Right, so I'll have 1 by 2 here, because h square has to be divided. So now you have this 1 by 2 and this 2 derivative. Now again you take the limit, correct? So this will turn out to be 2 f prime of x. So again that is another way of doing it, right? Because now if you take limit here, you will get this one. Okay, so I mean this is some way what you were thinking in that direction, that if you want to understand this, so this as some derivative, this as some derivative, and then it's kind of a difference of these two. Okay, so this is again going to be the second derivative. So in that way I guess this could be the proper way of reasoning it, using Taylor expansion. Okay, so this is another way maybe. So this, so maybe I should change the color. Okay, so now let's move to the next problem. Okay, so this is the kind of inequality that you have to prove. Okay, so that log of 1 plus x is bounded below by this x minus x square by 2 plus x3 by 3 minus x4 by 4, and bounded above by x minus x square by 2 plus x cube by 3. Okay, so I mean, so one way you already know, like that what you can do is you just take f, define f as log of x minus this thing, and then you check whether it's increasing or decreasing, and then you can conclude at this kind of inequality. But over here we will try to do it using the Taylor expansion. Okay, so we'll use the fact, we'll use to try to expand this logarithmic as a series. Okay, and we'll not write it as an infinite series, we'll just go to finite sum, because we just have to deal with these 4 terms and these 3 terms. Okay, so depending on what we want, we'll expand our Taylor series up to that term. Okay, so let's see how it goes. So suppose this f of x, I'm defining this f of x as log of 1 plus x. Okay, and okay, so let me write what Taylor series is. So Taylor series you can write in this way. So over here what we'll be doing is that I'll try to write this f of x. I'll try to decompose it uh, around the point 0. Okay, so this would be like, so by Taylor's theorem, so we know that this is C infinity, like you can differentiate it as much as you want. As far as you are going x, you are taking x to be strictly, let's say, greater than 0, then only. Okay, so here I should write x is strictly greater. Here you can take equal to as well, that's not a problem. But this inequality is just for x greater than 0. If you put x equal to 0, this will turn, you have to put equal to sign here. Okay, that's it, because all the three terms will become 0. Okay, so we'll just stick to x greater than 0. So by Taylor's theorem you can write this f as f of x is f of 0 plus f prime of 0 into x by x plus f double prime 0 x square by factorial 2 plus dot dot dot, you'll go till fk, let's say fk at 0 into xk by factorial k. Okay, and then what you do is the k minus 1th derivative, so f k minus 1, and here you will have theta times, there's something which is lying between 0 and x. Okay, because this zeta, so let me write in this way, this zeta, if you write this zeta should belong to 0 comma x, right? So this is nothing but you can write it as theta of x, where theta belong to 0 1. Okay, because this is straight line joining 0 and x. Okay, sorry. So what you have is, and then now it will be x k plus 1 upon k plus 1 factorial. Okay, very good. So since, okay, so over here you look that in this case we need till 4 and here we need till 3. Okay, so that means that for to get this inequality I would need to take k equal to okay, so here I am written k minus 1, it should be k plus 1. Okay, so here for this inequality I'll need to take k equal to 3, and for this one I'll need to take k equal to 4, right? Because here this sign of this term will determine the inequality. Okay, so till this one we want, right? So since I want x cube here, I'll put k equal to 3, and for this one k equal to 4, and this one I'll just try to see like what is the sign of this one to conclude the inequality. Okay, so this is how we'll proceed. Now to go there, we know that we need k equal to 4, that we need 5 derivatives. Okay, so let's see how the 5 derivatives. So first we'll try to find the derivatives of this f. Okay, so this f of x is log of 1 plus x, and this f prime of x would be 1 by 1 plus x. F double prime, if you do, you'll get minus 1 by 1 plus x square. F triple prime would be minus 2 by 1 plus x. Maybe let's write in this in short form, so you'll get 1 plus x minus 2 minus of, here f triple prime x would be 2 of 1 plus x minus 3. F 4x would be minus 6 1 plus x minus 4, and f 5x would be 24 1 plus x minus 5, right? Maybe here also let me write 1 plus x inverse. Okay, so this is how the derivatives of this function looks. So now we have to evaluate these functions at 0, right? So this tells you that f of 0 is 0. This tells you f prime at 0 is 1. f double prime at 0 is also minus 1, f triple prime at 0 is 2, f 4 prime at 0 is minus 6, and f fifth derivative at 0 is 24. Okay, so this is what we have obtained. So now let us take k equal to 3 and k equal to 4. So first let's go with k equal to 3. Then what we see that this log of 1 plus x is equal to, so f of 0 is 0, so we don't have to worry about that. F prime of 0 is 1, so I'll get 1 times x, plus f double prime 0 is minus 1, so I'll get here minus x square by 2, plus, and then for k, that third order derivative, f triple prime 0 is 2, so I'll get 2 x cube by factorial 3, and then at fourth derivative, so this would be k equal to 4. Here the k plus 1 will be 4, right? So what I'll get is plus f4, okay, f4 theta x, right? So f4 theta x is what? Minus 6 upon, so here it will be minus 6 upon 1 plus theta x raised to the power 4. This is my fourth derivative. From here I am writing this one. Okay, and then you have x raised to the power 4 upon factorial 4. So this is what we have got. So you can clearly see that this term is going to be positive. So because of this negative term, this whole thing is going to be negative. So what I can write it, this is less than x minus x square by 2, and now 2 upon 3 factorial will come. So this is 3 factorial is nothing but 3 times 2, right? So this 2 cancels, so I'll have x cube by 3, and this is 0, so less than 0, so I am just omitting that term. So this is what we have got. So this is nothing but this bound what we have written here. Similarly you can do for k equal to 4. Okay, so if I put k equal to 4, what I get is log of 1 plus x is equal to x minus x square by 2 plus x3 by 3, and then for the fourth one I'll get minus 6, and that x equal to 0, this will be also minus 6, and x4 by 4 factorial, plus now fifth derivative is 24 by 1 plus theta x 5, and then here you have x5 by factorial 5, right? This is what you have. Now again you can see that this term is going to be positive. Okay, so now I can write this as x minus x square by 2 plus x cube by 3, and here you can see this 4, I can write it as 4 into 3 into 2. Okay, so this will cancel out, so I'll have minus x4 by 4, and this is how you get this inequality. Okay, so this is how you can use Taylor's expansion, okay, to reach this kind of inequality. Okay, I hope this was clear.
Be extended. We have here stopped k equal to 3, k equal to 4, but it can also be extended.
Correct. So actually you can write the series of this. Okay, so since it has alternating series,
minus x.
Yeah, you can include much more. So maybe you can go 2 more here. So this is minus x4 by 4 plus x5 by 5. Like this also you can do. Okay, because this is infinite series. So here I am just using till k equal to 3 and k equal to 4, but you can get much, how should I say, much better bound. So you can obviously do that. In fact, what you can do is, see, the right hand bound is always going to be some odd power by odd number. Okay, so this log 1 by x, if you write it as series, the series form of this one is like this: x minus x square by 2 plus x cube by 3. So maybe I can tell in this fashion also. So what you can do is, if you go to the infinite series of this logarithmic, you can write this as x minus x square by 2 plus x cube by 3 minus, it has an alternating sign, minus x4 by 4 plus x5 by 5 minus x6 by 6 plus x7 by 7 dot dot dot. Okay, let me write one more, minus x8 by 8 plus dot dot dot. Okay, so what you are doing basically here is uh, so this is for x greater than 0, so x is always going to be positive. Okay, so now you are saying that this whole term is negative. By what I have written here, this whole term is sort of negative, kind of. That's why we can write log of 1 plus x is bounded by this quantity, right? So it's kind of, what you are doing is, in some sense, like you can pair this up, let's say. Okay, if you pair this up, it is nothing was minus x4. Okay, I should not say in that way. Okay, I should not say in that way. Pairing, I should not say. Okay, anyway, so what it basically says that for to get upper bound, you can bound it by any polynomial which ends with, I mean not any polynomial, alternating this kind of polynomial with odd power. And if you want to get a lower bound, you can do it by any even, you have to go till even powers. So you know this log is having this kind of expansion. To get upper bound, you can stop at any one. So maybe you can stop till, for upper bound you can stop till here, you can go till here, because you know the next term is going to be negative. Okay, in this case, and you don't care about this term, because in Taylor's you will just expand till finite terms. So you just care about this one. So once you see this negative sign, okay, this kind of negative sign, you get that this is always going to be less than 0, and once you see this positive sign, this is greater than 0. So you can get such bound always with higher powers as well. Here you can put any power. Okay then, okay, so let's go to the next problem. Okay, so over here you have been given that the double derivative exists, okay, and it is bounded on this positive real line. What you have to prove is that given that limit f is going to 0 for large x as x goes to infinity, you have to prove that this double first derivative also goes to 0, okay, as x goes to infinity. So this is what you have to prove. Okay, so again, what do you think? How can you deal with such problems? So in other words, what you can say that this f prime of x, you can make it as small as you want. Okay, this is what it means. If my f of x is very small, okay, and the derivative is, the double derivative exists and is bounded, then you can say such thing. Okay, so how do you think how one can proceed given these kind of condition? How can you think to proceed? So using fx, f double x, you have to conclude about f prime x. No idea. So how does this derivative looks like? If you want to write the definition of this f prime, okay, how will you write? So this f prime is nothing but f of x plus h minus f of x upon h kind of thing, right? So now can you think like how? So basically you have to write this in terms of this f double prime and f, right? This is what it means. So how do you get this kind of terms, or how do you get this f prime? you can again use the Taylor's theorem, right? Where if you use the Taylor's theorem, you'll get this f prime, and from there it seems that something can help, right? Because there you will have f also, f prime with f prime, you notice. Okay, so maybe if you think like this, right, the f of x plus h, how do you write? So you'll write f of x plus f prime x times h plus h square by 2 f double prime of x, like, I mean, okay, so let's say theta x, like this. Okay, so, or x plus theta h, sorry. Okay, now you see this is bounded. Okay, you know that. Okay, so how, maybe you will have to divide by h as well, because here you see this h is there, so you want something information about f prime. Okay, so suppose you divide by h, so you'll get h, right, and here you'll get h. Now you see this whole thing is actually going to 0, because my f is going to 0 as x goes to infinity. Okay, so we don't care about h, whatever h you choose, this whole is going to 0. This thing is bounded. Okay, this f prime is given to be bounded. Now for this to be small, you know that as h, if you choose h to be sufficiently small, this is also very small. So for this one, you know that if I choose my x to be very large, this is going to be very small. In this case, if you choose your h to be very small, okay, this whole term will be very small. Okay, so using these two facts, okay, what you can think that one can try that, okay, using these ideas, one can try to conclude that the f prime, this quantity, is also going to be very small for large x. Okay, so I mean, this is how one can try to prove. So here you see, you only need information about this f to be going to 0. Here you don't, you just need a bound on f double prime, and then using the smallness of h, you can say that this whole quantity will be very small, right? So we'll just try to go by this line. We'll try to use the Taylor's expansion and then try to see how to prove this one. Okay, so this is the main idea. Okay, so maybe so my goal would be to prove this to be very small. So what I'll do, okay, so let me write this as, that is, this for epsilon greater than 0, there exists x naught greater than 0 such that this f prime of x is less than epsilon for x greater than x naught. Okay. So this is what the definition says. Okay, so we'll try to prove this only. Okay, so for that, we'll choose epsilon. Okay, now again by Taylor's expansion, using Taylor's expansion, we have that f of x plus h minus is equal to f of x plus h f prime x, and then you will have plus h by 2 f double prime x plus theta h, right, where theta belong to 0 1. Okay, from here what I can write is my f prime of x is equal to f of x plus h minus f of x upon h, and here, okay, so here should be h square, and then you have minus h by 2, okay, and then f double prime x plus theta h. Okay, this is what you have. So maybe, yeah, so now, okay, so here the main thing is, what I need to make sure that this h, okay, so when I'm talking that this I want to make it as small as I want, so I don't want to use sort of help of h, right? Because this h is something which is coming in intermediate thing. Okay, so what I'm saying, okay, this is bounded, I know. So let's say this is less than equal to m. Okay, this you can see, like how should I say this, maybe. So okay, so using, let me write first and then I'll tell you. So using, so you know this limit x going to x is, sorry, infinity, this f of x is 0, right? Using this thing you can say that this whole fraction goes to 0 as x goes to infinity. So for large x this is very small, and whatever h you choose, so here h has no role, whatever h you choose you can say that this is very small. But over here I have to use somehow h, right? But you should not use h, because what you have to prove is this one here. If you see here, nothing like h is involved, right? In this, what I need to prove, h should not be playing any role, correct? So we have to somehow not use it. Okay, and then let me think. I just thought that okay, this in this way one can do it, but now I think this h I cannot use, I should not use it. Just a second. F prime of x, something has to be done. Just a second. So x plus theta h. Okay, so let me write this first. Using this limit x going to infinity, or I can say that f of x plus h minus, or just like this, limit x going to infinity, f of x plus h minus f of x upon h is 0 for any h greater than 0. Okay, so this I can say that this ratio by h, I can make it less than epsilon by 2 for x greater than equal to x naught. I mean, so that is, there exists x naught greater than 0 such that this happens. I'm just using the definition of this. Okay, but here the thing is that depending on this h, okay, my x naught will change. That is clear. Okay, but how does it help? So this is not a problem. So this part I can make it as small as I want, that is not an issue. But for this one, just a second. So okay, anyway, so let me just try to write, let's see how it goes. So what we have is that this h by 2, okay, f double prime x plus theta h, okay, this my goal is that I would like to make it less than epsilon by 2, so that this whole thing adds up and give me epsilon. So I know this is less than equal to h m. So let's say I'm saying that f prime is bounded by m and then by 2. Now I know that this is less than epsilon by 2 if my h is less than epsilon by m, right? Okay, okay, I got it. So see, if my h is less than this, then I have this one. So what I'll do now, so okay, so this is kind of back calculation what I'm doing here. So now I'll choose, so choose h greater than 0 such that h is less than epsilon by m. Okay, I'm choosing this one. Okay, then f of x plus h, I know, or like what I can write is then f prime of x. Okay, I can write it in this way. F double prime x plus theta h, right? I can write this first derivative f prime in this fashion, right? So initially I have chosen my h to be like this one, right? So we have this epsilon, okay, and we know the m because I know that the f double prime is bounded. Okay, so maybe this bound is, I am assuming this to be m. Okay, so now I am choosing my h in this fashion, then I know that my f prime can be given by this. Okay, how this is choice is coming, this choice is coming from here. Okay, but anyway, so I am choosing my h. This is true, actually this is true for all h greater than 0, right? This is what we have seen using Taylor's expansion. This is true for all h greater than 0. So I am in particular choosing my h to be sufficiently small, then my f prime is like this, correct? So maybe I can write here, so this is for h, any h greater than 0, right? Okay, so here in particular for this kind of thing I am getting this kind of expression for my f prime. Okay, now I can clearly see that this my f prime of x is less than epsilon by 2 plus epsilon by 2 for x greater than equal to x naught, right? So this is from maybe this one, 1 and 2 I can write, so 1 and 2. So what I can say is my f prime of x is less than epsilon for x greater than equal to x naught. Okay, so this choice of h what I am choosing is sort of intermediate. Okay, so it's not appearing in my final uh, approach, because this expression what I am getting for f prime, okay, this expression is true for any h. So I am choosing my h to be sufficiently small, that's all, because any h, I mean, so what will happen is basically, I mean, how should I say, so this f prime you can see this has many expression, right? If I change my h, my I mean the way I can look my f prime is becoming different. I mean in the sense of my values. This f prime is something which is fixed, okay, but this is something which is not fixed. This is changing depending on h. So what h I choose, this is changing, but ultimately it is fixed. I mean because my left hand side is a fixed quantity. So as I am changing h, this is fixed. Okay, so ultimately for small h, my f prime has this expression, that's it, and then I can say that this is less than epsilon. Do you get it? Yeah, this is fine. Okay. Okay, so this is how you can establish this kind of result. Okay, now let's come to this problem. So suppose you have been given a function f which has a local extremum at some point c. So extremum basically means it has either local minima or local maxima at the point c. Okay, then the question is which of the following is true. Okay, so what do you think? What about the first option? No idea?
Option A and C, one and the same, sir.
No. They are completely different. The first option guarantees you that the derivative will exist. The second thing, the C option is telling you that if the derivative exists, then it has to be 0. Did you get the difference? First option is telling you that the derivative exists. Third option says that okay, derivative exists, then it has to be 0. So they are completely different. Okay, then what do you think?
May not exist.
May not exist. Okay, so you are saying this option is wrong, the first option.
Yes, sir.
Do you have some example? Okay, so indeed this is wrong. Okay, but do you have some example in mind? Okay, so let me give you an example. So consider the function mod of x. So let's say f is from -1 to 1 to r, given by f of x equal to mod of x. So where is the minimum of this function? What is the graph of this mod of x? This is the graph, right? So this is -1, this is 1. So minimum, you know that it exists at 0, correct? So you can say 0 is a point of extremum, correct? But what do you think? The derivative, you know that f prime 0 does not exist. Okay, so the first option is wrong. So this suggests you that second option is correct, because you can think of this point 1 as well. So this is the point of maxima, but you know that the derivative exists. So derivative may or may not exist. So you cannot guarantee it, right? So this is true. Okay, now let's look at the C option. C option tells you that if f prime c exists, then it has to be 0. But we see here, right? So maybe this is the second point. We know that 1 is 1 and -1. Actually, both the points -1 and 1 are point of like extremum, right? Because they are the maximum value. So here it was minima, here it's kind of maximum. Maximum, right? But this f prime at -1, what is the f prime at -1? It is -1, right? And f prime at 1 is equal to 1. So here you know that the derivative exists, but they are not 0. Okay, so none of them is 0. So this option is also correct. Okay, what about the third option? So you notice here that the point is that here I am choosing the extreme value. Okay, in this particular example, we are choosing this extreme value, 1 and -1. Now the fourth option says that suppose the extremum value is attained at some interior point. Okay, for example, like this one here, 0 was the interior point, okay, where the extremum exists. So basically the minimum in this case. And it says that suppose c belong to AB, that means the local point is the interior point, and the derivative exists. Okay, then it's saying that the f prime will be 0. What do you think about this option? Clearly the counter example what I gave is not holding, correct? Because the 0 is the interior point, like 0 belong to -1 comma 1, but f prime 0 does not exist. So this option is not, this example is not correct for this example, right? So what do you think? Is it true or false? Any guesses? Haven't you seen this kind of result? Okay. Actually it's true, and maybe you can prove it in this way maybe. So suppose that C is a point of maxima. Okay, similarly you can deal with the minimum point as well. So I'll do the one case maybe. So suppose C is, so this is case 1 maybe. Okay, C, how should I say, that F has a local minimum at C, okay, belonging to AB. Then you know that F prime exists. Okay, so now let me, F prime is what? F prime of C would be limit h going to 0, or okay, let's say x tending to C, f of x minus f of C upon x minus C. Okay, and this is equal to limit x going to C plus f of x plus C, sorry, f of x minus f of C upon x minus C, and same as the left hand limit, x going to C minus f of x minus f of C upon x minus C. Okay, very good. Now you tell me, in this case, like since C is a point of minimum, so f of x, so here what do we mean? So we are taking C, x is from this region, right? X is larger than C, so clearly we can write in, so this is C. Okay, so then this denominator is strictly greater than 0, right? Also C is a local minima. That means if you take any point in a neighborhood of C, in a very small neighborhood, okay, local means like you cannot go beyond, in a very large, you cannot talk about a large interval, but anyway, since we are dealing with the limit, we only need a small interval which is covering C. So in this small interval, this is the local value, right, at C. So it's like this one maybe. So at C it's the minimum, and in the neighborhood it is taking the bigger value. So clearly this one, f of x, would be larger than f of C. So this is again greater than 0. Okay, so this whole quantity is strictly greater than 0. That means that the limit is greater than equal to 0. Similarly, in this case, you see that we know that this fx minus fc is going to be greater than 0. Just the same reason, because if you take x which is in the neighborhood of C, then fx will be greater because C is the minimum. And this one will be negative, right? Because x you are taking from the left, so it is less than 0. So this whole quantity is a negative quantity, and when you are taking the limit, it will be less than equal to 0, right? So what does this say? This says that this both are equal. That means they will agree only if both are 0, right? So this tells you that f prime of C will be equal to 0. Did you get this argument? Yeah. So similarly you can deal with the, I'll not do it here, but you can similarly, f has a local maximum at C belonging to AB. Okay, you can do it similarly. Okay. Okay, so now let's come to this problem. So here you have been given f is a differentiable function such that f prime C is 0 for some point in the interior. Then what can you say? That f is a local maximum, local minimum, or none of these? What do you think? These are the basic things, I guess. I don't know. If you start this thing, which is the kind of where you study about the maximum, minimum of the function, like how to find it, these are the basic stuffs what you get to see. right? So when you try to find a point of maximum minimum, what do? You take the derivative, you equate it to 0, then you say these are the critical points, right? So these need not be maximum minimum, these are just the points where there is a possibility that this could be a point of maximum minimum, or there is one another thing called inflection point, or where like it's neither maximum point or not minimum point, right? So these are some of the basic things what you see. So this could not be maximum or minimum, right? So this need not be true. Okay, so for example, you can take this example, f of x, or let's say f is defined from whole real line to whole real line given by f of x equals x cube, right? So what is the derivative? F prime x would be 3x square. Clearly f prime at 0 is 0, but you know that 0 is not a maximum or minimum point, it's called inflection point. That is the terminology what I think that is used. So the graph you can clearly see it's like this. So this is not a maximum nor a minimum point if you look, right? So this is a example where, so you can just say that this C would be a point, critical point. It could be maximum, it could be minimum, or it could be inflection point where neither maximum nor minimum occurs. Okay, so that's all for this problem. We don't get this page. Okay, so now let's come to this one. Okay, so here you have been given a function, and then you have to basically check, okay, which point is a point of maximum or minimum for this function. Okay, you have to look for the local maximum, local minimum. Okay, so what you can do is, so let me write the solution. So f of x is given to be x minus 1 square and x minus 3 cube. Okay, so this is your function. Now to look for maximum minimum, as I was saying, you just try to find the derivative. So f prime of x, if you calculate, what you get is, let's say x minus, we differentiate this first, we'll get 2x minus 1 x minus 3 whole cube plus 3x minus 1 square x minus 3 square. We take x minus 1 x minus 3 square common, what you get is 2 x minus 3 plus 3 x minus 1. So what you get is x minus 1 and here you get 2x and 3x will add up to 5x minus 6 minus 3 minus 9. Okay, so this is what you get. This is how the derivative looks. Now if you equate it to 0, what you get is x is 1. Okay, so x is 1, or x is equal to 3, or x is equal to 9 by 5. Okay, so there are different tests, like you can use the second derivative test as well, correct? But what I'll be using is a much simpler. So just this, using the first derivative only one can conclude. So you have to draw the sign scheme. Okay, so these are the critical points, right? So 1, and this 9 by 5 will be lying between 1 and 3. So let's say this is 9 by 5 and this is, let's say, 3. Okay, now look at the signs of the derivative. Okay, so f prime, if you take 1 less than 1 in this term, you can see this is negative, this is also negative, right? You just put x equal to 0, right? So what you get is, this is negative, this is negative, correct? So this sign in this region will be positive. So these are sign of f prime. Okay, so this is positive here, fine. Now if you take x which is lying between 1 and 9 by 5, so clearly this will be positive, right? Because it's greater than 1. This is anyway positive, so we don't need to bother about this. But this will be negative, so this sign over there will be negative. Okay, very good. Now let's look at this in the third region over here. You see, this is positive, this is positive, and this is anyway positive. So here you will have positive. Similarly, in this region it will be positive. right? So what we see is that here there is no change of the sign, so derivative. Okay, so what does this mean? Let me write the okay, so here I can write the implication. So in this region, f prime is always greater than 0, right? That this means that f is increasing in this region. Over here f is decreasing, over here f is increasing. Okay, so what does this mean? So here it was increasing and suddenly now it's decreasing, right? So increase and then decrease, so this will be point of maxima, right? So this tells you, so maybe I can write it here. So here I can write is that x equal to 1 is a point of maxima, local maxima of f for f. Okay, and here you see it's negative, so it decreases first and then it starts to increase. So 9 by 5, okay, x equal to 9 by 5 is a point of local minima for f, and this 3 is a point of inflection, so it's 9, so there is no change, it's increasing. Okay, so these are the 2 points of local maxima and local minima. So in this option this one is correct, right? Okay, f as a local maximum at 1. Okay, if this is clear, then maybe we can proceed to the next problem. So again you have to calculate this limits. In this one actually the b and c are almost like same, like what we have did earlier. You just take log and then deal with it, just use L'Hopital. So maybe this I will not do, so take log. If time will remain then I'll do this, but else I'll not do. So take log and use L'Hopital. Okay, that's it, nothing much to do. But for the one you have to do a bit of, you basically have to expand it, because you see, although this is 0 by 0 form, if you look at this term, so this x is going to 0, that means this is 0 and this is going to be infinity, right? So this term will converge to e, because it's 1 raised to power infinity form, so this is going to e and this minus e, so this numerator is 0 and the denominator is also 0. So this is 0 by 0 form, but like you have to, if you can calculate the derivative of this, then it's okay, but for me it would be a bit difficult to do all this. So I'll go by the expansion. So I'll try to expand this quantity and then see how it goes, I mean how the expression will come. Okay, so I'll do this a part. Okay, so this 1 plus x, so let us just focus on this quantity first. So 1 plus x raised to the power 1 by x. Okay, so this I can write as exponential and log of 1 plus x by 1 by x, right? So I'm just again using the help of log, but in a different way. So this is what I'll get, correct? Now I can use the property of log. So what I get is, this is exponential of, so 1 by x I can take like in this fashion, and then I'll have ln 1 plus x. Okay, so this is how 1 plus x raised to the power 1 by x looks. So now I'll try to expand this one. Okay, and you remember that I'll have to take x going to 0. Okay, so that we have to keep in mind. So let us try to expand this one. Okay, so 1 by x, maybe I can first write somewhere else. Okay, let me write it here again. I'll use this series expansion. So ln of 1 by x I can write, so I'm expanding it about x equal to 0, right? So what I get is ln of 1 plus, okay, so let me say this is fx, ln of 1 plus x. So I can write f of x as f of 0 plus, here x is greater than 0. equal to 0, and then I'll have f prime 0 times x. Okay, now see here, I have to look for 1 by x times log 1 plus x. Okay, and then rest will be some constant times x square plus some constant times x raised to power cube, and that's all. So this I can write, this is the order of x square. What I mean from here, so what I can say is that f of x, I can divide it by x. So f of 0 is anyway 0, so this is nothing but, and f prime at 0, if you calculate, it is going to be 1, right? Because 1 by 1 plus x, and that is going to be 1. So this is nothing but x plus order of x square. Okay, now if I divide by x, so 1 by x log 1 plus x is coming out to be 1 plus order of x, right? Okay, so you understand what, okay, so you don't have to worry about this higher order as well. So this is just like, maybe if you want, I can write to be a simple. So f double prime at some point zeta, let's say, okay, where zeta is lying between 0 and x, and then you will have, what do I say, this x square by factorial 2. Okay, so this f double prime xi by 2 factorial is some constant that we know. Okay, because f prime, if you see, it is 1 minus 1 by 1 plus zeta square. So okay, so this I am representing by some constant. So maybe if you want, I can write this f double prime. Okay, zeta also, if you want, I can write it as theta x, okay, by 2 and then x square. So let's go more precisely. Do you have some question?
Sorry, sir, by mistake.
Okay, no issue. So this is theta x. So this is how this f I can write. So I can write this as 1 plus f double prime theta x upon 2 into x square. Okay, so theta is lying between 0 and 1. Okay, so this is how my this 1 by x log 1 plus x looks like. Okay, now I can write this exponential. I can now use the expansion of exponential. So how does this make it? Exponential of something, right? So e raised to power x is nothing but, how do you write? So 1 plus x square by factorial 2 plus x cube by factorial 3. This is how you go, right? So over here I can say this is 1 plus, okay, and then, okay, for first, what I can do is maybe let me see, should I write exponential first, or yeah, okay, so let me write in this way. Okay, so it's 1, and let's not do it right away. Okay, so what I can do is maybe, so let me write exponential of, I'll write this one. So 1 plus f double prime theta x by 2 times x. Now you can see this is exponential of 1 plus this. So I'll just take exponential of 1 out. So I'll get exponential of f double prime theta x by 2 times x. Okay, yeah. Okay, so now what I can do is, I'll have to take logs. Okay, so now I can use the exponential. So I can write this as e exponential, I'll write 1 plus, okay, this f double prime theta x by 2 times x. Maybe I can go a bit down, and then plus f double prime theta x by 2 square into x square by 2 factorial plus so on, right? This is how I can write this. So okay, now I think it's okay. So now I can multiply this to get e plus f double prime theta x by 2 ex plus f double prime theta x by 2 square x square by 2 factorial e. So maybe I can take this as this times e. Okay, now what I can do, now I'll just try to write the given function, right? So recall what was the given function, 1 plus x raised to the power 1 by x minus e upon x. So now I'll take this on the left hand side. So what I'll get is 1 plus x raised to the power 1 by x minus e, and then you divide it by x. So you'll get this is equal to f double prime theta x by 2, and then you have e plus am I doing it right? Hope so. Okay, and then here everything will be, yeah, so maybe f double prime theta x by 2 whole square, then you have 1 by, okay, so maybe I can take x common from here, x, because x will be divided on the, like you have to divide it by x, so I'll get x by 2 factorial plus, maybe I can take x outside as well, okay, whatever, but then something, and then all the terms will have x, right? Okay, so I'll just write dot 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 times e, but I know this goes to 0 as x goes to 0, so that is the most important thing. Okay, so as x goes to 0, this is going to 0. Now, so this would imply that as you take limit x going to 0, this 1 plus x raised to the power 1 by x minus e upon x is equal to, now f double prime is again a continuous function, right? Because f double prime, if you calculate, f is this one, so f double prime is, let me write, f double prime of x would be minus 2 or 2, minus 2 by 1 plus x whole square, right? No, 3, right? This is my double prime, f double prime. So this is a continuous function, maybe I can write it here. So this is a continuous function that we have, so you can take limit inside, so it will converge to f double prime of 0 upon 2 times e and then 0. Okay, this is the limit value what you are getting. Now f double prime 0 is going to be 2, so it is going to be 1, so this is e, right? I hope I have written it correctly. F prime x would be minus 1 by square. Oh, I think I have written it wrong, sorry. This is not double derivative, it is 1 by x only. So you see f prime of x would be 1 by 1 plus x, and f double prime of x would be minus 1 by 1 plus x whole square, right? So I have written it wrong. So f double prime at 0 would be minus 1, so this will be minus e by 2. So this is going to be value of the limit. Okay, again, like here, as I was mentioning, that if you want, so here you see I have tried to write this as a whole series, but you know that this exponential can also be written just till this one, maybe, if you want, because you see here the only useful term what you can see is this only. Here onwards everything is going to 0, so you can expand this exponential just till this one, and then this term will be some derivative, double derivative of some zeta times x square by 2. That is enough, you don't need this also. But anyway, here I have written in this series form, okay, because you know that this is not playing any role, this will eventually go to 0. So generally you just expand up to what you need. Okay, here just expanding till 2 will be okay, just you here it will be just some triple derivative or double derivative of exponential at some zeta times x square by factorial 2. So you don't need x cube by factorial 3 and all. Okay, but anyway, so this is how you can deal with such problem. Okay, for the other two, as I mentioned, you just have to take log and then use L'Hopital. So I am leaving it to you. Okay, now let's come to this problem, 10th one. Okay, so over here what you have to basically do, so here you have been given that this limit exists and this limit is equal to 1. Okay, so you have to find the proper choice of a and b for which this is true. Okay, this need not be true for any a b, we'll see. Okay, so here also, like, both the problems are basically the same. Okay, you have to do so this whole problem is based on L'Hopital. Okay, it would be very easy if you use L'Hopital rule. Okay, so we'll see, maybe so I can solve one of them. Okay, so let's try to solve the b part. It involves 3 variables. Okay, so b part, so what has been given to use is limit x going to 0, x a plus b cos of x plus c times sine of x upon x raised to the power 5 is equal to 1 by 60. This is what you have. Okay, now let us try to evaluate this limit. Okay, so you see, if I put x equal to 0, this is 0 by 0 form. So I can use L'Hopital to get Lx tending to 0. In the numerator I'll have x and then I'll have b sine of x minus sine of x. So minus b sine of x plus a plus b cos of x, right? Fine. Here I'll have c cos of x. In the denominator I'll have 5 x raised to the power 4 is 1 by 60. Okay, now you see, as x goes to 0, this is 0, right? This term, okay, so let me first write it in a more simpler way. Limit x going to 0, you can club this and this together, right? So what I have is minus b x times sine of x plus a plus b plus c cos of x. Okay, and then I have 5x raised to the power 4 1 by 60. Okay, now you see, if you put x equal to 0, this is 0 anyway, it's fine, but this one is turning out to be a plus b plus c. Okay, and if it is not 0, suppose a plus b plus c is not 0, okay, in that case what this left hand side is going to be infinity, because the numerator is a plus b plus c and this is going to be 0, so it is a plus b by c times 0, which is infinity, right? But you know that the limit is 1 by 60, it is a finite quantity. Okay, so that means that to make sense of this limit, this a plus b plus c has to be 0, so that this becomes 0 by 0 form, and again we can use L'Hopital to proceed further. Correct? So here, from here I'll get so the first condition what I'm getting is, maybe how should I write, so let me write in a line, then it would be easier. If a plus b plus c is not 0, then the limit on the left does not exist, or I should write does not exist, or I should write is not finite, cannot be finite. Finite, so a plus b plus c must be 0. That is a plus b plus c equal to 0. So this is the first inequality, first restriction what we are putting on a, b and c. Okay, nice. So now now we know that this is a plus b plus c is 0, so again this is by 0 form. So here I'm using L'Hopital. Okay, so again I'll use L'Hopital over here because this is 0 by 0 form. So now what I get is minus b x cos of x. Okay, and then I'll have minus b sine of x plus 0, a will be vanished, and then here I have minus b plus c sine of x. In denominator we have 20x cube equal to 1 by 60. Now again you see minus b, I can write it here, so it will be minus 2b. That's it. So minus 2b plus c, okay, sine of x. Okay, now again if you see, this is a 0 by 0 form because here x is 0 and here sine will vanish, so it's 0 by 0 form. So again here again I am using L'Hopital. Okay, so again I'll use L'Hopital rule, and what I get now is minus bx sine x, so it will be plus, and minus b cos of x, and here I'll get minus 3, so maybe I can club it here, minus 3b plus c cos of x upon, I'll get 60 x square, 1 by 60. Okay, again same L'Hopital. Now you see again it is not going to be 0 by 0 form because this is 0 but this is turning out to be 1, so it will be 3b plus c. Okay, so this is the second condition, 3b plus c equal to 0. Okay, so again I'll use L'Hopital. So I'll get bx cos of x plus b of sine x, and just a second, plus b of sine x, and again it will be clubbed with this one, so plus 4b plus c sine of x, and then I'll have here 120x, which is equal to 1 by 60. Again the same L'Hopital. Now again if you see here, it is turning out to be, if I put x equal to 0, this is anyway good, this here is turning out to be 0 by 0 form, right? So here there is no issue, I can again use L'Hopital. So what I get is bx sine of x with minus sign plus b cos x, which would be clubbed with this one, so 5b plus c cos of x upon 120 is equal to 1 by 60 in L'Hopital. Now in the denominator we don't have x, so there is no issue as such. I'll just put x equal to 0. What I get is 5b plus c upon 120 is equal to 1 by 60. This tells you 5b plus c is equal to 2, right? Now I can use this 2, so this is the third equation. Now I can use 2 and 3 clearly to get b and c, right? So if I just subtract 2 from 3, so 3 minus 2 will give me 2b equals to 2, which will give me b equals to 1. Now what you can do is you can put b equal to 1 here, right? So this will give you, so this is you got b equals to 1. If you put b equal to 1 here, you will get c equals to minus 3, right? Now if you put b, value of b and c in the first one, and this whole thing will imply that a plus b plus c is 0, so a would be minus b and minus c, so which will be 3 minus 1 2, right? So this is the value of a, b and c, which if these are the value of a, b and c, then you will get that this limit is 1 by 60. Okay, so similarly you can do for a as well, the first part, the first one. Okay, so that's all for today. Okay, so do you have any doubt?
No,
Okay.
sir.
Okay. If not, then let's stop here. See you next week. Okay.